Lecture 8.4, Day 2, Tests for Convergence. This is a photo of Riverfront Park in Spokane, Washington. This is the site of the 1974 Spokane World's Fair. In the background is what remains of the United States Pavilion from that fair. The fair was built on the site of a former railroad yard, and the tower to the right is the clock tower from the former Great Northern Railroad depot. First, a little review. The integral from 1 to infinity of dx over x to the p, where p is greater than 0, and p is a constant. We have the integral from 1 to infinity of x to the negative p dx, which we can write as the limit as b approaches infinity of the integral from 1 to b x to the negative p dx, or the limit as b approaches infinity of 1 over negative p plus 1 times x to the negative p plus 1, evaluated from 1 to b. Inserting our limits of integration, we have the limit as b approaches infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. If p is less than or equal to 1, then b to the negative p plus 1 gets bigger and bigger as b approaches infinity. Therefore, the integral diverges. If p is greater than 1, then b has a negative exponent and b to the negative p plus 1 approaches 0. Therefore, the integral converges. For this integral, we have the integral from 1 to infinity of e to the negative x dx, which could be written as the limit as b approaches infinity of the integral from 1 to b e to the negative x dx, the limit as b approaches infinity negative e to the negative x, evaluated from 1 to b, the limit as b approaches infinity of negative e to the negative b minus negative e to the negative 1, or the limit as b approaches infinity, negative 1 over e to the b plus 1 over e. The first term approaches 0, so we get 1 over e. So this integral converges. Does the integral from 1 to infinity of e to the negative x squared dx converge? Compare 1 over e to the x squared to 1 over e to the x for positive values of x. For x greater than 1, e to the x squared is greater than e to the x. Therefore, 1 over e to the x squared is less than 1 over e to the x. If we look at the graphs of these functions, here's 1 over e to the x squared and 1 over e to the x. We see that for x greater than 1, e to the x squared is greater than e to the x. Therefore, 1 over e to the x squared is less than 1 over e to the x. Since 1 over e to the x squared is always below 1 over e to the x, we say that it is bounded above by 1 over e to the x. Since 1 over e to the x converges to a finite number, 1 over e to the x squared must also converge. The comparison test. Let f and g be continuous on interval from a to infinity, with 0 less than or equal to f of x less than or equal to g of x for all x greater than or equal to a. Then 1. The integral from a to infinity of f of x dx converges if the integral from a to infinity g of x dx converges. Or 2. The integral from a to infinity g of x dx diverges if the integral from a to infinity f of x dx diverges. Example 7. The integral from 1 to infinity of sine squared x over x squared dx. The maximum value of sine x equals 1, so 0 is less than or equal to sine squared x over x squared, which is less than or equal to 1 over x squared, on the interval from 1 to infinity. Since 1 over x squared converges, sine squared x over x squared converges. 1 over x squared, of course, converges because it's a p-series with p greater than 1. Another example, the integral from 1 to infinity of 1 over radical x squared minus 0.1 dx. Radical x squared minus 0.1 is less than x for positive values of x, so 1 over radical x squared minus 0.1 is greater than or equal to 1 over x on the interval from 1 to infinity. Since 1 over x diverges, 1 over radical x squared minus 0.1 must also diverge. If functions grow at the same rate, then either they both converge or both diverge. Does the integral from 1 to infinity dx over 1 plus x squared converge? As x goes to infinity, the 1 in the denominator becomes insignificant, so we compare it to 1 over x squared. If we take the limit as x goes to infinity of 1 over x squared divided by 1 over 1 plus x squared, we get the limit as x goes to infinity of 1 plus x squared over x squared, which using L'Hopital gives us the limit as x goes to infinity 2x over 2x, which is 1. Since 1 over x squared converges, being a p-series with p greater than 1, 1 over 1 plus x squared must also converge, because the two functions grow at the same rate. Of course, the integral from 1 to infinity of dx over 1 plus x squared, which we could write as the limit as b approaches infinity of the integral from 1 to b of dx over 1 plus x squared, can be evaluated as the limit as b approaches infinity of the inverse tangent of x from 1 to b, or the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 1. Looking at the graph of tangent x, as y approaches infinity, x approaches pi over 2. Since we're looking at the inverse tangent function, the inverse tangent of b approaches pi over 2. The inverse tangent of 1 is pi over 4. So we get pi over 2 minus pi over 4, or pi over 4. The integral from 1 to infinity of 1 over x squared dx is the limit as b approaches infinity of the integral from 1 to b x to the negative 2 dx, which is the limit as b approaches infinity negative x to the negative 1, evaluated from 1 to b, or the limit as b approaches infinity of negative 1 over b minus negative 1 over 1, as the denominator approaches infinity, the first term approaches 0, and we get 1.